This video demonstrates how to use a spreadsheet program while performing some basic near-surface refraction layer interpretation and statics computations. The description section of this video contains a link to the created spreadsheet. This video demonstrates the use of a spreadsheet, LibreOffice Calc, for simple manual statics or similar computations. All computations herein should be considered approximate. Whether the resulting statics are suitable for your data is your decision. If you are unfamiliar with spreadsheet programs, you should watch my video, Spreadsheet Uses, Dix Equation, Time to Depth. You should also watch that video if you are unfamiliar with Q files. Further, the video herein can be considered an extension of my video, Manually Deriving Refraction Statics for Simple Near Surface. I advise you to be familiar with that video before watching this video. I am starting from SPS2 files, but you do not have to. If you are looking at this video and creating your spreadsheet from nothing, I suggest you organize your columns the same way I do. Using the same columns in your spreadsheet makes errors less likely. Better still, I suggest starting from my final spreadsheet setup. You can find a link to the final spreadsheet in the description section of this YouTube video. You can also find a link to this presentation. You can also find copies in Seismic Unix, demos, sushiftcsv. In this video, I start from an SPS2S file, but you can also start from an R file. First, use one of these SUTool CSV setups to convert it to a CSV Q file. You may already have converted SPS2, S, or R files for geometry purposes, in which case the output CSV file will actually contain S or R records rather than Q records. You can input that file into the spreadsheet and easily change it to a Q file. The output Q file looks something like this. First, input the Q file. Since it is a CSV file, you see this. Use options separated by and comma. If your file actually has S records or R records, change these all to Q. The first 6 rows here do not mean anything to the LibreOffice Spreadsheet Calc, but you should maintain them if you want to use the output later in Seismic Unix. If you have converted your SPS2 S or R file using the previous SUTool CSV setup, then your spreadsheet looks like this. Now delete columns F, G, I, K, O, P, Q, R. Yes, delete G even though it may contain statics. The remaining values look like this. The line and point numbers, columns B and C, and the coordinates, columns H and I, do not get used in static computations herein, but retain them anyway. If you are making the spreadsheet from nothing, still put shot depth in column F, and shot uphold time in column G, and elevation in column J. And even if you are starting from an SPS R file or other receiver information, still put nearest shot depth in column F and nearest shot uphold time in column G. Change the names in row 6, columns D and E, and put your datum elevation and replacement velocity in all rows below them. Note, these values are usually constants, so they usually could be specified in only 2 cells in the spreadsheet. But having them in each row requires less explanation herein. Select cell K7 and type equal D7 minus J7 divided by E7 times 1,000. Then copy cell K7 to the remaining cells in column K. The results are simple statics computed purely from elevations. Select cell L7 and type equal D7 minus J7 divided by E7 times 1,000. Then copy cell L7 to the remaining cells in column L. Note this is the same computation as for column K. Only the names in row 6 are different: G-stat elevation and S-stat elevation. This indicates how I am going to proceed. In every row, I am going to compute various statics as if a receiver exists there, and also as if a shot exists there. If you are not familiar with LibreOffice Calc, note that copying a cell containing an equation into another cell results in adjusting the cell references in that equation, except if you use $signs to freeze the cell references. In cell M7, put equal D7 minus J7 plus F7 divided by E7 minus G7, and in cell N7, put equal D7 minus J7 plus F7 divided by E7, and then copy M7 to the rest of column M and N7 to the rest of column N. The results are simple Uphole statics, sometimes called field statics. The calculations above are receiver static equals datum elevation minus shot elevation plus shot depth divided by replacement velocity minus shot uptime. And shot static equals datum elevation minus shot elevation plus shot depth divided by replacement velocity. These simple computations make the assumption that the shot depth is below any top layer that might exist. Things get more complicated later in this video. Remember that in this spreadsheet, I am pretending that all rows contain both a shot and a receiver at the same location. So, for the receiver, it does not matter that the elevation value is actually the shot elevations. They are the same. It may appear odd that the shot uphold time appears in receiver computations and not in the shot computation. But signal did not travel through material above the shot, while the signal did travel through material up to the receiver. However, subtracting uphold time in receiver computation is an overcorrection. The uphold time needs to be adjusted by shot depth divided by replacement velocity. That is why shot depth also appears in the receiver computation. Now I continue with the intercept method of deriving statics. The intercept method is used in my video, manually deriving refraction statics for simple near surface. The intercept method is usually done while looking at shot gathers. If manually deriving statics using the intercept method, you usually just want to perform analysis at widely spaced locations, like every 40th point. Here, for illustrative purposes, I am deleting all but 3 rows, just keeping stations 102, 110, 120. Further computations need a top layer velocity, the weathering velocity. Use column O to contain it. I am putting an equal F7 divided by G7 times 1,000 in O7 to compute it from shot depth and uphold time for a situation that might exist. But your situation may require you to just guesstimate a value for it. If your shots are on the surface, then equal F7 divided by G7 times 1,000 cannot be put in column O. For that case, you must set the values in column O manually. Advice: a value you should definitely check is in column O. Column O contains the weathering velocity, the top layer velocity. The next values to check are in columns F and G. Column F contains shot depth, column G contains shot uphold time. Column F divided by column G produces a value for column O, but that weathering velocity value is often wrong. Near the end of this video, this is discussed in more detail in a section called Other Considerations Related to Shot Holes. For the intercept method, consider a shot on the surface of a simple near surface. The refracted arrival path is downward through the top layer, along the top of the next layer, and then upward through the top layer. Obvious note, a shot depth of 0 does not mean there is no top layer. It just means the shot is on the surface. For that simple surface shot case, this equation converts intercept time to top thickness, where ZW is weathering layer thickness, VW is weathering velocity, VB is the base velocity, the velocity under the top layer, and TI is the zero intercept time. Note that much of the literature about refraction layers introduces the velocity triangle and the critical angle and then formulates this equation and others in terms of sines and cosines. I am not going to do that. I do not want to define intermediate variables. The spreadsheet is going to contain plenty of variables already. So you need to determine this intercept time and this base velocity from a display of first arrivals. The intercept time is easy, and to compute the velocity, we just need 2 time offset points, near and far. However, unlike these fake traces, remember that recorded traces within the critical distance do not contain refracted wavelets, but they do contain a lot of other energy. So do not be fooled when choosing the near time offset pair. Use columns in the spreadsheet to contain your values from the first arrival display. These values are time near, time far, offset far. Also the velocity and the intercept, which the spreadsheet can compute from those time offset pairs. Enter some values for the time offset pairs. And in cell T7, put equal S7 minus Q7 divided by R7 minus P7 times 1000, and copy T7 to rest of column T. And in cell U7, put equal P7 minus Q7 divided by T7 times 1000, and copy U7 to the rest of column U. These computations yield velocity and zero offset intercept time. Note the specified equation in column U uses the velocity from column T. You can, of course, specify numbers for some or all cells in columns T and or U. In that case, the time offset pairs will be ignored for the velocity and the intercept. Now we have sufficient values for the equation seen previously. To compute the thickness of the top layer, in cell V7 put equal U7 divided by 1000 times T7 times O7 divided by 2 divided by the square root of the difference of the squares of T7 and O7. Then copy V7 to all subsequent cells in column V. Note I use the name ZW no hole since this does not consider shot depth yet. If the shot is in a hole, the top layer thicknesses of column V need adjustment. Next, I continue with how the adjustment is computed. But near the end of this video, there's a section called Other Considerations Related to Shot Holes. Consider a shot in a hole. If the shot is in the top layer, the shot end of the path contributes a smaller amount to the intercept time. This means the previous equation would compute the first layer thickness, that is the average of the shot end and the receiver ends. To get the true thickness, the shot hole depth has to be accounted for. For a shot in the top layer, since we've used a divisor of 2 in this equation, then we need to adjust the thickness value by summing half the shot depth. But if the hole is below the top layer, the intercept time only contains the contribution of the receiver ends. So if the shot is below the top layer, since we've used a divisor of 2 to compute the current thickness value, then the thickness value should be multiplied by 2. The choice wanted in the spreadsheet is, if the shot depth divided by 2 is less than the current thickness value, then add the shot depth divided by 2 to the current thickness value. Otherwise, use double the current thickness value. In calc, this can be accomplished by using the if function. In cell W7, put equal if bracket F7 divided by 2 is less than V7, comma, F7 divided by 2 plus V7, comma, V7 times 2, and copy to rest of column W. This means if the shot depth is less than the current thickness value, then set the true thickness value to half the shot depth plus the current thickness value. Otherwise, set the true thickness value to double the current thickness value. After doing that, notice that all values in column W are double column V. To make sure the if function is doing what is wanted, reset P9 and R9 so that F9 divided by 2 is less than V9. Now notice that W9 becomes V9 plus half of shot depth, as wanted. So now the layer thicknesses and velocities have been computed. Next, how are the statics computed from that information? It is helpful here to remember that statics are corrections for the reflection signals, not the refraction signals. The reflection signals did not go through the parts of layers above them when going down from the shots. But the reflections did go through those parts when going up to the receivers. The next diagrams indicate the static computations for one-layer situations. In the following diagrams, ED is datum elevation, VREP is the replacement velocity, EP is the surface elevation of a point P, DP is the depth of a point P, ZW is the thickness of the top layer, VW is the velocity of the top layer, VB is the velocity under the top layer. TP is the static time of a point P, either a shot or a receiver. Now, I'm not going to read through the equations in this situation, but I do point out that there's a diagram to the left which starts at the elevation of the datum and then goes down to the surface, where the shot is in this case, and then you can see the thickness and the velocities underneath that. So here, if a point is on the surface, then the depth equals 0, and the static is computed by these equations, which reduce to what is seen below. Green arrows point to the associated interval for the calculations. Now, if the depth is less than or equal to the weathering thickness, then the static equals this equation, which reduces to the equation at the bottom. If the shot depth is greater than the weathering thickness, then the static is equal to this equation, which reduces to the equation seen at the bottom. Notice that the second velocity is used in the last term below. You might consider dividing by the replacement velocity instead, but consider that this part of the reflection path for the receiver has not been replaced with the replacement velocity. So the path going up to the receiver has the velocity of the second layer in this part. I feel that the path downward from the shot should be corrected to that same second velocity. So in cell X7, put this to get the receiver static, the static at the surface. Then copy X7 to the rest of column X. In cell Y7, put this to get the shot static, the static at the point depth. Notice the if function in here, which decides whether the shot depth is greater or less than the thickness of the first layer. That is all I want to show about one-layer static computations. To use the results in various programs, you can output a CSV file. You can do that using Save As in Calc. The CSV option just outputs the numeric values themselves. But before you output a CSV file, if you want to use the output in Seismic Unix programs like sushiftcsv, you should maintain the top 6 Q file records. We have already given everything a Q file name in row 6. Now we should supply good Q file formats in row 4. So copy J4 to all cells to the end of row 4, K4 to Y4. Using the Save As CSV option, the output file looks something like this. This file is an acceptable Q file for shot statics in program sushiftcsv. It can also be used by program subinqcsv for 2D spatial interpolation using Grunloff shot point numbers, stations, and then by susmoccsv to perform 2D spatial smoothing. After that, sushiftcsv can use these Q files output by those programs. But the previous Q file is not an acceptable Q file in sushiftcsv for receiver statics. The problem is not with the receiver statics values in that file. The problem is with these Q names. These are shot keys. They need to be receiver keys for the receiver statics file input to sushiftcsv. For 2D surveys, you can often just change the names to Gronors, gaps, gx, and gy. Then re-output another CSV file and use it in sushiftcsv for receiver statics. Note that you do not need to change the Q file names for the statics values. The sushiftcsv program allows you to choose which Q names contain the shot and receiver statics you want to apply from the Q files. But sushiftcsv does default the static names it wants to apply to gstat and sstat. Notice that I do not use gstat and sstat as static names in the spreadsheet. That is because both receiver and shot statics are computed in the spreadsheet, and also because several types of statics are computed. The effect is to force you to specify which statics you want sushiftcsv to use. You can, of course, modify your spreadsheet so the final static values you want to use are named gstat and sstat, so the defaults of sushiftcsv will use them. For 3D surveys, you cannot just rename Grunloff to GRNS gaps because 3D receiver line point numbering is not the same as 3D shot line point numbering. However, coordinate numbering is the same. So SX, SY can be renamed to GX, GY to apply nearest statics using sushiftcsv, as done for the technique in my video, manually deriving refraction statics for simple near surface. The SHOT-Q file for sushiftcsv only needs the SHOT key identifiers and statics, or the SHOT key coordinates and statics. The receiver Q file for sushiftcsv only needs the receiver key identifiers and statics, or the receiver key coordinates and statics. If you want to reduce the size of output CSVQ files, you can do so by deleting columns that do not contain the values you want. But you need to do something before deleting those columns. You need to get rid of the spreadsheet equations and just keep the numbers. To do that, select every cell in the spreadsheet, click between A and 1 at top left, then Data, Calculate Formula to Value. Then delete the columns you do not want, and output using Save As CSV. Onward to two-layer computations. The intercept time from the first refractor was named Ti. I'm naming the next Tj. The velocity from first refractor was named Vb. I'm naming the next Vc. The top layer thickness was named Zw. I'm naming the next Zb. A shot in a hole, some names, and ray paths for a two-layer situation. Tj is this zero intercept time. To compute Vc, we need two time offset points, near and far. Note that the next layer velocity and zero intercept can still be obtained even when the refracted wavelets never become the first arrival. Tj is this zero intercept time. To compute Vc, we need two time offset points, near and far. However, unlike these fake traces, remember that recorded traces within the critical distance do not contain refracted wavelets. They do contain a lot of other energy, so do not be fooled when choosing the near time offset pairs. You can find the n-layer intercept time equation online. Unrolling the summation to two layers, substituting the previous definitions into it, and rearranging terms produces the following equation for thickness of the second layer. Note the first layer thickness value to use in this equation is not the true top layer thickness. It is the top layer thickness before adjustment for shot depth because neither of the intercept time values includes time from above the shot. Just to keep things a bit clearer, use column Z to indicate that layer 2 computations start in the next column. The values in this column are not used. Now add columns time near 2, offset near 2, time far 2, offset far 2, and columns for Vc velocity and Tj intercept that will be computed from these pairs. Put in some reasonable values for the time offset pairs, and then the computations shown here. And copy those to the rest of column AE and the rest of column AF. To compute the second layer thickness without considering the shot depth, in cell AG7, put that long equation, and copy AG7 to rest of column AG. And to compute the true second layer thickness, we need to distinguish which layer contains the shot. This requires using an if function inside another if function. So to compute the true second layer thickness, put this double if function in cell AH7 and copy AH7 to the rest of column AH. Note the previous if functions used the true top layer thickness value, not the top layer no hole thickness value. Note also that when the shot depth is within the layer below the top layer, These ifs are only adding half the amount between shot depth and bottom of top layer. This is because only the receiver ends of the path contribute fully to the TJ intercept. The shot ends of the path do not contribute the difference in time between the bottom of the top layer and the shot depth. This is analogous to the one layer case when the shot is within the top layer. The next diagrams indicate the static computations for two-layer situations. In the following diagrams, ED is the datum elevation, VREP is the replacement velocity, EP is the surface elevation of a point P, DP is the depth of a point P, ZW is the thickness of the top layer, VW is the velocity of the top layer, VB is the velocity under the top layer, ZB is the thickness of the layer under the top layer, VC is the velocity of the next layer, and TP is the static time of a point P, either a shot or a receiver. Again, I won't try to go through the equations, except to indicate that on the left is a diagram from the datum elevation downward. If a point is on the surface, then dp equals 0, and the static time equals the computation seen here, which reduces to the bottom equation. If the depth of the shot is less than the top layer thickness, then the static equals the computation seen here, which reduces to the equation at the bottom. If the shot is actually within the second layer, then the static is equal to this computation, which reduces to the equation seen at the bottom. If the shot is below both layers, then the static becomes equal to the computation seen here, which reduces to the computation at the bottom. Notice that the VC velocity is used in the last term below. You might consider dividing by the replacement velocity instead. But consider that this part of the reflection path for the receiver has not been replaced with the replacement velocity. So the path going up to the receiver has this VC in this part. I feel that the path downward from the shot should be corrected to the same velocity. To compute the two-layer receiver static, put this in cell AI7. Then copy AI7 to the rest of column AI. To compute the two-layer shot static, put this double if in cell AJ7 and copy AJ7 to the rest of column AJ. We have already given everything a Q file name, row 6. Now we should supply good Q file formats, row 4. So copy J4 to all cells to the end of row 4. That's K4 to AJ4. Then, to output a CSV Q file, use the procedures shown previously. Next, some example tests. Spreadsheets make testing relatively simple. You can find a link to the final spreadsheet in the description section of this YouTube video. You can also find a link to this presentation. Also, you'll find copies in Seismic Unix demos directory sushiftcsv. This example is in row 7 of the spreadsheet. A shot in a hole with depth 16, layer thickness is 40 and 30, and velocity is 100, 1,000, and 10,000. Since the velocity contrast is high, the path ends are nearly vertical. The time vertically through these layers at their velocities. The shot uphole time, and the remaining vertical time under the hole. Since path ends are nearly vertical, TI intercept time is approximately 240 plus 400. And TJ intercept time is approximately 240 plus 30 plus 30 plus 400, which is 700. Using the n-layer equation seen previously and a calculator, the exact TI intercept time is 636.79, and the exact TJ intercept time is 699.67. Using those values in row 7 of spreadsheet yields a true weathering thickness of 40, as it should, and a second layer value of 30, as it should. This example is in row 9 of the spreadsheet. Now I change the shot hole depth to 52, which is deeper than the top layer. Note that the dotted red line indicates a ray path through the layer. If the shot depth was far enough below the top of the layer, this would cause trouble in determining the velocity and intercept time using time offset pairs. If you do suspect that the shot depth is far below the top of the layer, then I suggest you use far offset traces to make an estimate of the velocity and intercept and derive a preliminary value for the layer thickness. Then correct the offsets in some near time offset pairs using the preliminary value for the layer thickness. That should improve the estimate of the layer velocity and thickness. For this example, using the n-layer equation and a calculator, the intercept times are 397.99 and 447.74. Setting 52 as shot depth and 412 as uphole time, notice we get 126.21 as the top velocity. This is because the VW computation in column O is simply depth divided by uphole time. The spreadsheet does not know that VW is 100. But we know that VW is 100, so reset it to 100. Often you have to guesstimate a VW value or guesstimate the thickness or both. Entering some reasonable time offset values to produce VB and VC velocities and TI and TJ intercept times, we get the correct ZW and ZB thicknesses. This example is in row 11 of the spreadsheet. A slightly different example, less top thickness and less shot depth. Since ray path ends are nearly vertical, TI is approximately 100 and TJ is approximately 24 plus 30 plus 100. Entering this example into row 11, we see that VW is computed wrong because the uphole time traverses part of the next layer. Setting VW to known value of 100 produces approximate thickness and other values. Remember that we use the approximate intercept times for this example. This example gives you some idea of how sensitive the results are. This example is in row 13 of the spreadsheet. A more realistic example. The ray paths are not approximately vertical. Using a calculator, TI is 16.94, TJ is 54.53. Setting time offset pair values so they produce VB, VC, and TI, TJ values, and also setting VW to 610 and entering the rest of the realistic example, we get the correct layer thicknesses. So far, the examples have been used to check the computation of velocities, intercept times, and layer thicknesses from time offset pairs. Next, the examples are used to check the computed statics values. Returning to the first example, spreadsheet row 7, manual computation of the one layer static for a point on the surface gives, and the one layer static for depth 16, which is within layer 1, gives that value. Continuing with the first example, row 7, manual computation of the two-layer static for a point on the surface gives that, and the two-layer static for depth 16, which is within layer 1, gives that answer. And we see those static values in columns X, Y, and AIAJ. In the second example, spreadsheet row 9, manual computation of the one layer static for a point on the surface gives, and the one layer static for depth 52, which is below layer 1, gives that answer. Continuing with the second example, row 9, manual computation of the two layer static for a point on the surface gives that, and the two layer static for depth 52, which is within layer 2, gives that answer. And we see those static values in columns XY and AIAJ. In the third example, spreadsheet row 11, manual computation of the one layer static for a point on the surface gives, and the one layer static for depth 16, which is below layer 1, gives that answer. Continuing with the third example, row 11, manual computation of the two layer static for a point on the surface gives that answer, and the two layer static for depth 16, which is within layer 2, gives that answer. And we see those static values in columns XY and AIAJ. Remembering that row 11 uses approximate intercept times. In the fourth example, spreadsheet row 13, manual computation of the one layer static for a point on the surface gives that answer, and the one layer static for depth 18, which is below layer 1, gives this answer. Continuing with the fourth example, row 13, manual computation of the two layer static for a point on the surface gives that answer, and the two layer static for depth 18, which is within layer 2, gives that answer. And we see those static values in columns XY and AIAJ. End of comparison between manual computations and spreadsheet. You can, of course, perform other relatively easy manual tests by changing datum elevation, point elevation, and replacement velocity. Other considerations related to shot holes. Is the shot hole depth less than the top layer thickness? If you have been told that the shots were drilled to less than the bottom of top layer, then the top layer velocity in column O is just shot depth divided by shot uphole time. Is the shot hole depth the same as the top layer thickness? If you have been told that the shots were drilled to the bottom of the top layer, then the top layer velocity in column O is also just shot depth divided by shot uphole time. And the top layer thickness in column W can be set to shot hole depth. Is the shot hole depth more than the top layer thickness? If you have been told that the shots were drilled to below the bottom of top layer, then the shot uphole time and shot depth are not sufficient to compute both the top layer thickness in column W and the top layer velocity in column O. You have to guesstimate either top layer thickness or velocity. If you have not been told that the shot is within the top layer, then the shot uphole time and shot depth are not sufficient to compute both the top layer thickness and the top layer velocity, because the uphole time may be a sum of times from the top layer velocity and part of the next layer's velocity. Some advice. It has been my experience that information about simple shot uphole times and shot hole depths is quite approximate and unreliable. It may be better to guesstimate the top layer velocity value even if you have values for shot uphole times and shot hole depths and have been assured that the drill stayed in the top layer. But you might also have more information to resolve the top layer problems. An uphole survey might have been done. An uphole survey consists of drilling different holes and putting special geophones down those holes to record the signal from a shot down that hole. The time the signal takes to travel between the downhole geophones allows computation of velocities. A change in velocity also allows picking the bottom of the top layer. So an uphole survey means you may be able to directly specify top layer thickness and velocity. No need to determine the intercept time at all. But if the holes of the uphole survey are too shallow, you still need the intercept time to determine the top layer thickness. Remember, for uphole surveys, the actual seismic shot still may be on the surface. So be careful with the shot depth values in the spreadsheet. The upholes can be used to compute some layer velocities and thicknesses, and the actual seismic shot's time offset pairs to compute other layers. Some advice for 3D surveys follows. First, note that all statics computations are the same for 3D surveys. However, for 3D surveys, to use program SU-bin-Q-CSV for spatial interpolation, you need to have locations that form enclosing rectangles. One way to do that is to use the same locations as for velocity analysis, VLANs. See my videos about bilinear interpolation and VLANs in mutants. But you should understand that the VLAN locations are CDPs. You will also need to use traces near those CDPs to perform the intercept method within this video. Usually, the intercept method of interpretation is done while looking at shot gathers. To do that, you need to find shots near the VLAN CDP's cell coordinates. There is nothing that prevents using the intercept method on the super CDPs of traces made by the SU-bin-big-CSV program, as done for VLANs. But, of course, the traces to use should not have undergone as much processing as for VLANs. Since these super CDPs contain traces for multiple shots, this means the interpretation will not be exact for any shot. But average interpretation is desirable if you are going to assign the statics to nearest shot and nearest receivers using the sushiftcsv program, and then resolve the statics using the surescsv program. This is discussed in my video, Manually Deriving Refraction Statics for Simple Near Surface. Thoughts on intermediate datum. First, to clarify what I am referring to herein by intermediate datum. An intermediate datum is not the same as a floating datum. A floating datum is essentially a smoothed version of the total statics at a CDP. A floating datum does not change the total static shift of any trace. See my video about floating datum. An intermediate datum does change the statics. You will have noticed that the thickness of the bottom layer is not set herein. An intermediate datum is a constant or varying elevation you decide to specify. That elevation is used to produce a thickness for the bottom layer. Typically, the velocity assigned to that thickness is the bottom layer velocity. Using the thickness, the difference between that assigned velocity and the replacement velocity produces a time, which is added to the statics. Why use an intermediate datum? Consider a 2D survey with some reflectors. A typical assumption is that deeper structures follow surface topology, approximately. So, the reflectors below should have a similar physical shape as the surface. If this green line is the bottom of the near surface, and we use a replacement velocity that is similar to the velocity below the near surface, then the static should correct the traces to produce the approximate shape of the reflectors. Now, remember that the replacement includes the difference in elevation up to the final datum elevation, as well as the thicknesses of the near surface layers, as shown at 2 example locations below. But what if the reflectors do not follow surface topology? That's when it might be beneficial to use an intermediate datum, constant or varying. By replacing some additional thickness, rather than just the near surface layers, The resulting trace statics should produce the approximate shape for this situation. We have a reasonable velocity from the last near-surface layer, but not a thickness. The intermediate datum elevation allows us to compute a reasonable thickness. I'm not going to put an intermediate datum computation in the spreadsheet. I'll leave that as an exercise for you. Assuming the shot depth is above the bottom layer, a procedure could be use next column for intermediate datum elevation you want. Use next plus one column for velocity you want, probably just a copy of the bottom velocity. Use next plus two column to compute the intermediate datum thickness from the surface elevation, layer 1 thickness, layer 2 thickness, and intermediate datum elevation that you put in the next column. Use next plus 3 column to divide the thickness in next plus 2 column by the replacement velocity column, and subtract the same thickness divided by the velocity in column next plus 1. Use next plus 4 column and sum column next plus 3 with previous receiver statics. Use next plus 5 column and sum column next plus 3 with previous shot statics.